All right, good morning. We are officially 10 minutes behind schedule, so hopefully people will start trickling in, but that was a fun keynote. I had to leave early, so hopefully the last demo was as interesting as the first one. So welcome. This is the second day of reInvent. It's our first conference we've ever done. It's been a blast for those of us involved in organizing it. I almost wish I was a participant, because there's about 20 other talks I'd like to go attend, but I don't get the chance to. So my name is Deepak Singh. I'm the principal product manager for Amazon EC2. Specifically, I work on instances. Any instance type, how the EC2 instance platform works, is the kind of work that I do, the teams that I work with. And what I'm going to talk about today is essentially how you can use Amazon EC2 instance types, how we think about building and designing instance types. You heard about 2 new ones this morning. I'll talk a little bit about those. The philosophy about how we think about resources, and a little bit about how you as customers should think about an instance and how you should be using it. Warner very correctly this morning said that if you design things the right way, when new instances become available and new capabilities become available, you can upgrade automatically. So for most of you, your compute infrastructure looks something like that, or hopefully very few of you by now. There was a time that I actually sat next to a room with more racks than this. But one of the reasons I fell in love with EC2 many years ago was that my compute infrastructure looks something like that. It's an API call away. Everything, as so eloquently stated multiple times this morning, is programmable. And when you have programmable resources, you can do a lot of interesting things. But today, here we are here to talk about instances. And to me, an instance is a fundamental unit of compute that Amazon Web Services offers. When you think about doing stuff with a CPU, doing stuff in a computational environment, how can you do it and how should you be thinking about it? And the way we provide you is building blocks, and we call them instances. My friend Dave Brown would call them primitives that allow you to get work done. And what does an instance consist of? It has multiple things. We give you a certain amount. It has CPU. It could have disk, memory, network. These are all the components that we package together and give you an instance. It looks like a server, but you shouldn't be thinking about it like a server, because you can do more interesting things with it. For convenience, we tend to cluster these into instance families. It's not just a convenience for nomenclature purposes. It's actually how we think about when we go back to the dashboard and say, OK, we need to create an instance type or a family of instances that satisfy a certain requirement. How can we build them together? What the size of that family should be? And how do we couple them and combine them for people to consume easily? Before we go there, let's take a trip back into the past. I don't know how many of you were around looking at Amazon in 2006. I remember I was already an S3 user. I remember seeing a blog post by Jeff Barr, whose blog's been a great source of information for years, about this thing called Amazon EC2 that Amazon had released. And after scratching my head for a few minutes about what Amazon was up to and why my favorite bookstore was providing servers that I could spin up and down, this was pretty fascinating, and about a day later, I was actually running on Amazon EC2 on the one instance type that was offered at that time, which was the M1 small. I actually think the page probably looked different then, but I did have a cache of it. The M1 small was a very simple instance. It had less than 2 gigabytes of memory. It gave you one EC2 compute unit. Now, on our website, we define EC2 compute units as a 1.1 gigahertz 2007 Xeon. I'd like you to forget that. I think the way to think about an ECU, and I'll come back to that, is just a unit of compute of an M1 small. It gave you some amount of storage and some amount of I/O performance. And voila, with the API call, there was no console at that time. All you had was an API. I was able to log into a server, and I had to compile some old code that I had lying around. I didn't have the right Linux server at home at that time. And we're off to the races. But things change. What used to be a page with some amount of information now gives you a lot more information. The default up here already suggests that there's more instance types than just an M1 small. We tell you how much memory you have. Each instance essentially gives you this kind of information. We tell you the computational power. As I just said a few minutes earlier, the way to think about what an EC2 compute unit is that a small is 1. So if you have an application that you can benchmark against a small, and it goes 2x faster on your, or requires 2x the resources than a small provides, you're better off using, and probably better off using something with this ECU rating of 2. I think that's how I think about it, is use M as your baseline and compare to that. what the actual speed is. Doesn't really matter that much. We give you some amount of instance storage. These are storage on the instances. When you stop or terminate that instance, the storage goes away. So you have to remember that. It's not persistent. It's only available for the lifetime of that instance. This actually also includes instance reboots. A lot of people forget that when you reboot an EC2 instance, you come back on the instance is still alive, and the storage is still active and available to you. All EC2 instances actually available in 64 bits now. Some, like the M1 Small and a couple of others, are also support 32-bit. We give you some notion of the network I/O performance of an instance. This includes everything from traffic to the internet, traffic to other instances, traffic to S3, EBS, etc. And we have this new feature that came out a few weeks ago, and I'll talk a little bit, a couple of months ago now. I'll talk a little bit more about it later in this talk, but we call this EBS-optimized. And a subset of instances support this capability. And what it really gives you is the ability to provide dedicated additional network capacity, getting used to wearing an earpiece, to Amazon EBS. And for the case of an M1 large, what it tells you is you have 500 megabits a second between EC2 and EBS. This does not interfere with any other traffic you're doing. So your instance-to-instance traffic, your instance-to-network traffic go through the original network that you have. And if you launch the instance with this flag that says EBS-optimized, you get this dedicated pipe, essentially, to EBS with the quality of service of throughput of about 500 megabits per second. The goal is to provide more reliable traffic between EC2 and EBS, and it works really well with EBS provision IOPS volumes. So till Werner's announcement this morning, here are all the EC2 families that we have, and I'm going to walk through all of them and the kinds of applications they're useful for, and how we optimize and the kind of features on these that we optimize for. So these are divided into 7 families. Standard, high CPU, high memory, micro, cluster compute, cluster GPU, and high I/O. The names sort of suggest what kinds of applications and what kinds of profiles you should be thinking about. Let's go through them one by one. Standard instances, there's 4 of them. There used to be 3. Earlier this year, we added the M1 medium. The way I like to think about them is that they have hit a sweet spot for a number of resources. Let's go back one slide. If you take a look at all these instances, other than the M1 Small, they give you slightly less than 4 gigabytes of RAM per virtual core. So an M1 Medium has almost 4 gigs of RAM, a single core. An M1 Extra Large has 15 gigs of RAM and about 4 cores, which means to me, and a certain amount of disk, and the ECUs essentially scale linearly. So an M1 Extra Large is 8 times as powerful as an M1 Small, and so does the pricing. That 4:1 ratio is a really, really nice sweet spot for applications. For example, M1 Medium is remarkably popular for lots of people who want to use just a single Windows instance. They want to run a Windows server. It gives you 1 core and 4 gigs of RAM. They love it. It's a great entry level for Windows. The kinds of applications that people run on these today include everything from databases, especially on the larger instance types, because you have sufficient amount of memory. You have EBS-optimized support now on both the extra large and the large. Lots of people use them for caches. Netflix, for example, on their Cassandra layer, till recently, used a fleet of M1 extra larges as the caching layer on top of their Cassandra infrastructure. Lots of people like using them for data processing. I think you saw a little bit in the Animoto talk, although they moved to high CPU instances. If your applications require some amount of memory, more than the high CPU instances provide, these are a good data processing environment. They're relatively cheap. But processors evolve. The M1 family has been the workhorse of Amazon EC2 for a very, very long time. But technology improves. So the thing that we did just a month or so ago was take advantage of some of these technologies and launch what we call the 2nd generation of standard instances, what we call M3 standard instances. They come in 2 sizes, extra large and 2 extra large. And if you look at the M3 compared to the M1, they provide you a similar balance of resources. They have about 4 gigabytes of RAM per virtual core, so 15 gigs on the extra large for 4 CPUs, which is exactly the same as the M1 extra large. The difference is your ECU rating goes up from 8 to 13. So per core, you have 50% more CPU capacity, and we also have an option that gives you double the core. So there's just taking advantage of how technologies evolved, some software changes that we could do, we are able to provide you a new generation of instances, still at a pretty low cost. Actually, the M1 extra large at 58 cents, when we introduced these, we dropped the prices of the M1, but this is cheaper than the M1 extra large used to be. So as I said, 50% more CPUs per core, 8-core option. You probably noticed there's no disk in this instance. It's all EBS based. And what kinds of applications are people running on them today? Fitting batch processing. This is actually a remarkably powerful instance. You can push, you can do a lot of processing because of the fast CPUs. It's not just fast CPUs, you actually get great memory bandwidth. So you can actually put, if you're encoding, there's no disk on this, but you can actually, there's enough for the 8-core instance with almost 30 gigs of RAM. You can actually start pulling in files into memory and encoding from memory, which is really, really quick. And the other application that people use these for are web servers and content management systems, where you need to drive more throughput, where you need to serve requests faster. So it's a great family for that purpose. So the way to think about it is the M1 is a lower cost instance. It provides a lower entry point. You have smaller instance sizes. So if you're running a distributed application that requires just a single core, you want it at low cost, you want to scale out, this is great. But if you have need for speed, as they say, you need more cores, the M3 instance provides sufficiently fast resources for you. One of the things to remember is, some people might ask, is how do we go from M1 to M3? M2 was taken. So we had to, when we went to second generation, we had to call it an M3. Didn't think far enough at the time. This is an instance that some people, it's a misunderstood instance sometimes. And what I'll try and go through in the micro instance type is talk about the kinds of applications that you want to run with micro instances. So what is a micro? It is a low-cost instance. In fact, it is the basis for the EC2 free tier. So if any of you are using the EC2 free tier, you can essentially run a single micro instance for a month continuously for free, for if you're a new EC2 customer for a year. What the micro provides is a low consistent baseline, it's a very low consistent baseline, but occasional bursts of CPU capacity, but these are not, some people think that you can burst as long as other resources are available. That's not the case. You can burst for a short period of time, and then we throttle you down, and you cannot burst again for a certain period of time, and then you can burst again. So how can you run? If your application profile looks something like this, it actually fits in very nicely with the micro. You burst, then you sit down, then you serve another request, you come down again, and you go up. So something that's request-based, serving up a few requests every now and then works really, really well here. But there's a certain set of profiles to avoid. I've run into a lot of people who try and run Hadoop on micros. It's not a good idea. What happens is, if you're running sustained for a period of time, you get punished. And you get sent down to the trough for a longer period of time than you would unless you were serving up requests occasionally. We actually are trying to make sure that everybody's getting their fair share of resources. So if you're trying to run for a long period of time, we can't do that. So we put you in a penalty box. So that's one way of doing it. We've made some optimizations that the penalty box is shorter duration than it used to be, but that's something to avoid. And those other profiles, if you look at it, the one at the bottom, it's almost, if those things are frequent enough, it's almost flat. But when you're trying to serve up too many requests, please.
Is the penalty box only applied to micros?
Only to micros. So one thing to remember is for every EC2 instance, CPU is hard scheduled. You get a fixed amount of CPU. There's no oversubscription. There's no sharing of CPU resources. The micro is the exception to that. Yeah. And by the way, feel free to ask me questions in the middle. I don't mind. So that's a micro. It's very, very useful if you're running a small blog, if you're running a small website, you have this thing that wants to serve up a listener every hour. Every hour it wants to do one thing, or every few minutes. It's perfect for that. Yeah?
You could avoid that penalty box if you put CloudFront in front of it.
So if you're serving up those kind of requests for your assets, absolutely. That's why I think a lot of people think micro is serving up all the requests and there's no asset somewhere else. You're completely right. In fact, a lot of people run blogs like that, right? Where they'll keep their server. They're not very high traffic blogs. They occasionally get hit and they have to serve static assets. Those will be coming off the edge. That's not uncommon, absolutely. One of my favorite EC2 families, in fact, the one that I've probably used the most myself over the years, is the high CPU family. When we add the word high and we have a CPU or something after that, it means that that particular resource is the ratio of CPU to memory in this case is favorable to CPU. It's a higher ratio. So the focus and this is where we get onto the focus of how we design these things. Our focus with the high CPU family is providing you low dollar per core and low dollar PCU. We optimize to see how can we provide you a really low computational capabilities and what kind of trade-offs can we make to get you there. So in the case of high CPU, the trade-off that we made when we released this was to provide low memory. So you essentially have a 1 gig per core ratio of resources. So if you have a memory-intensive job, it's not going to work. If you're CPU-intensive and you're not memory-bound, it works really, really well. And it is the cheapest instance that we have for CPU-bound applications, other than the big cluster instance. And I'll show some graphs on that later. You get it in two choices, C1 mediums and C1 extra large. The C1 medium, as a lot of people have found over the years for batch processing, is the most cost-effective, is an extremely cost-effective option. If you compare it to the M1 large, they both have one. Compared to the M1 small, for example, you get double the CPU, but more than double the CPU power, and the pricing is not double. So it's really, really effective. And if you saw, I think it was Animoto talk this morning, they talked about how they were sending some jobs to C1 medium because they were stranding resources on the C1 extra large. It does save a lot of money there. Ideal for scale-out applications. If you just want to do batch processing and keep adding nodes as you need to do more, or if you're running a web server fleet, C1 extra large is excellent. This is the typical pattern for a lot of our applications that run in C1 extra large. You have a set of tasks, a job queue, and as the queue fills up, you just scale the instances out, and you're done with your job. It's rinse and repeat. It's probably the single most common pattern that I've seen, especially historically on EC2. You can scale this up massively. This is a company called Cycle Computing. I think they might have done a few talks at reInvent, where they can scale to 50,000 cores globally to screen ligands. And it's purely done on, mostly done on C1 extra large instances. This is their scaling up. That's the heat map of what work is being done on instances. And they just add nodes as more work comes through. Just keep adding, keep adding, keep adding. They have automated processes that do that. Since most of these jobs are stateless, essentially each node is a dumb worker doing work. It's cheap, it works out, and scales beautifully. So if you're doing batch processing or if you're running a web server fleet, I would definitely recommend C1 extra larges. Are very, very common and very, very cost-effective for those applications. But what if you need even more performance? I mean, the C1 has only a gig a core. It's 20 ECUs at the largest. Things get even faster. C1's great for scale-out. But what about more tightly coupled applications as well? Or no more network-bound applications? A few years ago, we launched the cluster compute instances. What are these instances, and how can you use them? The first thing to remember about cluster compute instances is they're the only instances that we provide where we tell you what processor you're running on. So the current cluster compute instance is the second generation, the CC2 8 extra large. You're running on two Intel Xeon E5-2650 2670 processors. These are Sandy Bridge processors at 2.6 gigahertz. They have 16 cores, so 2 sockets, 8 cores a socket, 32 threads, because we turn hyper-threading on. You get 88 elastic compute units with a CC2. So if you compare it to an M1 small, that's 88 times faster. It's not 88 times the cost. It costs $2.40 an hour. The other thing that we did when we launched CC instances was to put them on a 10 gigabit Ethernet network. And we tell you you're on a 10 gig network. But what makes this network more interesting is the concept of a placement group. A placement group is just an abstraction. When you create a placement group and you launch instances into it, in this case, I have launched 64 instances into a placement group of type cluster, which is the only strategy that we support right now. You're not just getting a 10 gig network, you're getting a 10 gig network with full bisection bandwidth, which means that all instances within that network are talking to each other at full 10 gig, no oversubscription, no completely non-blocking network. It was our way of saying, of abstracting out what would traditionally be called a high-performance cluster, where you're getting a full bisection bandwidth. And this just allows you to essentially add capacity to your cluster with an API call. So once you've created your placement group, it's essentially a container. You want more nodes into participating in the cluster, you just add them to it. What does this allow you to do? So about a year ago now, when we launched CC2 instances, we ran a 17,000 core job, LinPack job. That's 1,064 instances. We got a peak performance of 240 teraflops, which at that time, and this is the best result a geek could ever want, We were the 42nd fastest supercomputer in the world. The way supercomputers go, right, every 6 months they update the list, and things get faster very quickly. We are now at 102. But the beauty of this was that you could provision a supercomputer with essentially a few clicks and be able to run HPC-style applications very quickly. If like me, you've spent many, many years applying for grant time to get onto a supercomputer, it's really, really rewarding and it makes things a lot easier. We were working with some friends at Intel at the time, and they nicknamed this thing the Beast because of how quickly it could scale and how stable it was and how inexpensive it was compared to other supercomputers in the top 100. In fact, when we launched this was the only Ethernet-based supercomputer, and still is, in the top 100 supercomputers of the world. But that's a big machine. What's something more practical? You can actually get into the top 500 supercomputers today, as in the latest list that came out in November, with a 330 instance cluster. Not that big. It still gives you 76.9 teraflops at less than $800 an hour. And if you run it in spot instances, you can do it for less than $90 an hour. This was based on the spot price on the 17th of November. On demand, my friend Jason Stowe from Cycle calls this on-demand utility supercomputing because it basically takes away the need for you to apply for grant time, get into a queue, find a supercomputing center somewhere, and do interesting stuff. And this is an example of somebody doing matrix calculation, doing 1 billion matrix doubles in just a few minutes. And what makes this possible? How can you do it so quickly? This is why we tell you what processor you're on. The Sandy Bridge family has an instruction set called AVX. It's a 128-bit instruction set that does double the flops per cycle of previous Intel generations. So you get really, really good performance out of it for floating point calculations.
Is that a Xeon?
It's a Xeon. It's an E5 2670, a Xeon E5. And in fact, we launched them before the E5 got released publicly. So we were available in November, and the public release of Sandy Bridge, I think February or March. And so we have 3 instances where we tell you what you're on. They're 2 Nehalem-based, and this is Sandy Bridge-based. It's not just for HPC. A good example of the kind of performance you can get for non-HPC applications is Druid, which is a database a real-time database that's provided by MetaMarkets. I believe it's open source now. And they were being able to, with a 100-node cluster of these, were doing 26 billion rows a second, partly because of the high bandwidth between the nodes. And you get 64 gigs of RAM per instance as well, and about 3.5 terabytes of storage. We are planning to add some new features to it. These aren't available yet, but over the coming weeks, we'll add 2 new features without a change in price. One is, so you just get them. You'll have to restart your instance to do it. One is you get Intel Turbo, so you'll be able to go beyond 2.6 gigahertz. So you'll be able to get more than 88 ECUs of power if there's resources available to give that to you. And we'll also support NUMA, which allows you to take advantage of memory affinity. And for many applications, gives you a 10 to 15% bump just by affinitizing memory properly. The second instance is sort of in the cluster family is the cluster GPU instance. You heard a little bit about it this morning. It takes advantage of GPU pipelining for general purpose computing. It's an older processor. It's Nehalem-based, Xeon 5570s. But the thing that you get with it is 2 NVIDIA Tesla M2050 GPUs. This is the previous generation of Tesla, but you get a ton of compute power on a single instance using the CUDA programming language, which is a programming library that NVIDIA released. But we also support OpenCL, ACC, et cetera. An example of the kind of performance increases you get, Amber is a molecular dynamics package that comes out of the academic community. On a CC2 8 extra large, which is this big beast that I talked about, the line in the middle, that's the amount of nanoseconds of simulation you can do in a day. The one on the right is using the CG1 4 extra large. You can do significantly more computing for the kind of application because it fits into that paradigm really well. And it costs actually less than a CC2 does. It's $2.10 an hour. So if your application can be converted, you have to rewrite apps. You have to write them in CUDA. If your application can be pipelined, you can fit your data into the memory that the GPU provides. You get tremendous speed up. The other instance family that we have is a high memory family. Again, as I said, high memory would indicate that the ratio of memory is higher in this case. We are biased to that. And what we try and focus on here is how much cost per RAM we can provide you. These are the cheapest instances per RAM that we have today. And so if you're a memory-bound application, we recommend that you run here, which means a lot of databases, for example. We have 3 instance types, the extra large, the 2 extra large, and the 4 extra large. The largest one has about 68 gigs of RAM. And those are the prices. They scale linearly. They have pretty fast CPUs as well. So they're very popular with people who want to run reasonable performing databases. But also for caching, lots of people run Memcached on these instances, and also for in-memory computing. You'll find a number of in-memory databases that people run on AWS that tend to take advantage of these instances. So what else could we do? Werner stole my thunder. I wasn't sure he was going to talk about these this morning. So we just announced, pre-announced a cluster high memory instance. It's not available yet, but it will be in the coming weeks. This instance has 2 Xeon E5-2670s, so it's the same CPU performance as the CC2 instance. It has 240 gigs of memory, of really fast memory. It has 2 120 gig SSDs, 10 gigabit Ethernet, and it supports NUMA and Turbo. It's designed for memory-bound systems, so memory affinity is really useful, and we give you as much CPU juice as we can from a Sandy Bridge processor. So it's going to be maybe that we should call it the bigger beast or something like that. We don't have a suitable nickname. The applications that we expect people to run on it are things like HANA from SAP. SAP runs HANA right now on EC2 and CC2 instances. My guess is once they get hold of these, given the amount of memory that they get, they'll be supporting these. The folks running Druid will probably get significant more benefit from running in this. Anybody doing real-time in memory analytics, this is kind of why we designed this instance. Before I go ahead, I'm more than happy to take questions on this one right now, if anybody has any. Otherwise, we can do them later. We can also use them for memory-intensive HPC, where you have large data sets that you just want to keep them in memory, or just scientific computing in general. So hopefully the instance will be available in a few weeks. And how much does it cost? Something Werner did not talk about. So it's $3.50 an hour on demand. And if you take the effective cost of a 3-year heavy utilization reserved instance, it's 90 cents an hour, which is about the same price as our SSD instances. So that's our first new instance type that we announced earlier this morning. And again, it's designed for people with lots of memory-intensive calculations. So what about disk I/O? We just talked about memory. People have often complained about disk I/O and EC2 for a long time. We provide instant storage. We do have EBS for people running databases. One of the requests I've heard very frequently from customers over the last year or so has been, give me a lot of low latency IOPS, which means that network attached storage is not going to work because the latency is too high. And I want over 100,000 IOPS, and at a relatively low cost. I don't want to go buy a disk array from somebody that's going to cost me an arm and 3 legs. So the best solution for those happens to be SSDs. And so we announced earlier this year high I/O instances. This is an instance that's SSD backed. We give you lots of CPU as well, and lots of networking. It is on a 10 gig cluster network. Today, the high I/O instance can give you about 120,000 4K random read IOPS and about 85,000 4K random write IOPS. On demand, it is $2 and I've actually forgotten how much it is. I think $2.10 an hour or something like that. No, it's actually $3. And on reserved instances, it's 90 cents an hour if you're doing a 3-year heavy utilization effective price. So the thing to remember is this is SSD backed, so it has the properties of write performance in SSDs, where depending on how you're using the active LBA span, your write performance can actually vary quite a bit. But what is it good for? It's really good for replicated databases. Remember, this is on instance storage. So if you shut the instance down, the data is gone. So you have to run something replicated. And it's really, really good for NoSQL. About 70 to 80% of our customers using these are probably running Cassandra or MongoDB on them today. This is Netflix's, right? The day we launched it, I think Adrian had a blog post where just without any tuning, they ran Cassandra on it. What they found was that the read request latency went from 10 milliseconds to about 2 milliseconds. And their 99th percentile request latency went from about 65 milliseconds to 10 milliseconds. Werner talked about 99th percentiles today. I think that's really important. So they were about to halve the system cost for the same throughput.
That is using what?
Our high I/O SSD-backed instances.
The one that is released today?
No, this has been around for a while, about 6 months. The other architectural change they made was they used to have a bunch of M2 4x large high memory instances fronted by an M1 extra large caching layer. They got rid of the caching layer, and they went from about 48 M2 extra larges to 15 HI1 4 extra larges. So significant change in how their Cassandra architecture worked. We've seen many other customers adopt exactly this, for Cassandra in particular. For MongoDB, I'm not a Mongo expert, so I don't know what a Mongo op is. But this is work that Tengen did. They were doing running tests with MongoDB, and they were able to essentially serve up 64,000 Mongo ops at 245 megabits a second at really very low variability, very consistent performance. So if you're running a NoSQL database, or actually there's folks running pretty much every kind of database on it as long as they can replicate, the high I/O instance is designed for serving up lots of IOPS at very low latencies. And because you can cluster them, you can do a lot of bandwidth, network-intensive performance as well. So on the higher end, so you have the cluster instances for compute, you have the high memory instances, cluster high memory for memory-intensive stuff, and you have these for I/O-intensive applications. While we're speaking of I/O-intensive applications, I should talk about EBS-optimized instances, which I talked about a little earlier. They are designed to be used with EBS-provisioned IOPS volumes. For those of you who don't know what an EBS-provisioned IOPS volume is, I don't remember if I have slides on that. It's a EBS volume type where you can upfront tell it with how much I/O you want from that volume. So today we support up to 2,000 IOPS from a single volume. So you provision that volume and say you want 2,000 IOPS, and we try and deliver that 2,000 IOPS to you. That's on the server side. If you want consistent client-side performance, remember, the network interface on EC2 is shared between a whole bunch of things. This option allows you to essentially get dedicated network throughput to EBS, so it gives you much more consistent performance. We support two kinds right now. You get a gigabit for M1 extra large and M2 extra large, and you get half a gigabit for 500 megabits a second for the M1 large. And over time, we'll add more instances that support this capability. Just as a note, the cluster instances, so the HI1, the CC2s, all have tons of bandwidth. So you don't have this feature on there, but you can use them with EBS-optimized instance provision IOPS volumes at scale pretty well. So the way to think about it is, if you have applications that need 20,000 IOPS, for example, you want to use provisioned IOPS instances and EBS-optimized, provisioned IOPS volumes with EBS-optimized instances. They're more manageable. There's flexibility. You don't have to get all those resources if you don't need them. You can get small data storage. But if you need a whole lot of IOPS, you need low latency, and you need tons of bandwidth between instances, that's the instance type to go. Andy talks about DynamoDB being the fastest growing service we've had. If you counted high I/O instances as a service, they would be the fastest growing service we've had. The adoption has been just off the charts. And there's one more thing. Again, Werner kind of stole my thunder. But as has been evident from this conference, there's a lot of talk about data. I hate the word big data, so I'll use data. People are collecting data at faster volumes than ever before, more data than ever before, and hopefully using them for useful operational decisions, business decisions. And for that, we created a new instance type that's also coming in the coming weeks, called the high storage instance. A high storage instance has 16 virtual cores, 35 ECUs, so very similar CPU spec as the SSD instances that I talked about. They have 117 gigs of RAM on an instance. They have the 10 gig Ethernet network, that cluster network that we have talked about a few times. But the key is you get 24 individual hard drives. They're just provided to you as 24 devices. That's what you get. Each hard drive is 2 terabytes, so you get 48 terabytes of storage. So if you have applications that need to do lots of sequential I/O, where you care about storage depth and that's the throughput that you get out of these things to the CPU. 2.6 gigabytes a second of throughput from disk to CPU, which is significantly more than any other EC2 instance today for sequential I/O. So what kinds of applications? If you're running a very large Hadoop cluster, where HDFS is really large, or petabyte scale Hadoop cluster, hey.
How much are they going to need?
I'll tell you in a second. Yeah. Hi, Bill. So today, if you have a very large Hadoop cluster and you're running HDFS persistently, the best option you have is EC2 8 extra large instances. But they only have 3.5 terabytes of storage on them. So you have to over-provision instances, over-provision CPU to get the right storage depth. This changes that. So if you're running Hadoop, large Hadoop clusters, awesome. If you're doing data warehousing, absolutely awesome. So if you're doing MPP type systems, this is the instance, and you have very large data warehouses, this is the instance type that you want to use. So it's designed for very, very large data sets. That's what it costs. So on demand, it's $4.60 an hour. If you're using a 3-year heavy utilization ROI, it works out to be about $1.40 an hour effective. So again, if you care about dollar per gigabyte, if you care about dollar per gigabyte per second of throughput, that's the instance you want to use. Let's go back down memory lane. So we talked about Amazon EC2 having a single instance back in 2006. Probably a few people in this room have been using it for that long. Today we have 17 with these two instances that we just announced. And if you summarize what I was trying to talk about is, your Amazon EC2 instances are our measure of compute. If you want compute capacity from AWS, you can measure them in chunks. And the chunk that we have today, Reed had some interesting requests to Andy yesterday, which were kind of fun. But today it's the Amazon EC2 instance. They come in a bundle of sizes across many, many families. And we try and optimize these for a particular use case. Now, having said that, every instance type that we ever released has been used in ways that we did not expect. That just gives us ideas for new ones. That's kind of what happens. And we're always very interested in figuring out what you want. So I'd say, in the words of an old knight in Indiana Jones and the Last Crusade, choose wisely, because if you, we recommend that you benchmark your application on different instance type, figure out which one provides a sweet spot between what you want to achieve, the cost that you want to achieve, and the performance that you want to achieve, and satisfy your customers. There are some people who would rather run on 100 M1 smalls than on a few CC2s, because for their application design, that works better. It's a nice application with limited coupling. For others, the CC2s work better because of the floating point performance. These are the kinds of calculations that I recommend people do. The one on your left is the dollar per ECU for every instance. You'll notice that the CC2.8 extra large is the cheapest one that we have. Actually, the C1s, yeah. And the C1s are just a little bit more than that, but maybe you don't need 32 cores for your application or a 10 gig network. And then you can look at things like dollar per RAM. I may not have the new instances in here because I didn't, but high memory instance would be the cheapest for that then. And then you can look at dollar per storage and try and make decisions on whether you need to use the high storage instances. And we're always interested. As you heard from the SSD stuff, the requirement was not, give me an SSD. The requirement was, I want lots of IOPS at low latency. And we try and make the right decisions for our customers to try and figure out what's the best, most cost-effective option for them that meets their requirements. And as you have seen over the last 2 years, we've kept adding a micro on the low end, upgrading our first generation standard to a second generation, take advantage of new processors, and added many, many, many more higher end instances for bigger applications, quite honestly. So thank you very much. I'll hang around. I'm happy to answer any questions. And